Okay, so here's the premise of the first demonstration, okay, is that in theory, and I don't know if you guys have thought about this, right, isn't atoms are largely what?
Nothing.
They're largely nothing, empty space, correct? If we blow an atom up to the size of the Rose Garden Arena, the nucleus is the size of a grape. Well, it depends on what atom you're talking about, or if it's uranium, it's actually quite large, you know. But it's like the size of a grape, and it occupies the center of the Rose Garden Arena, and the electrons are buzzing around at the edges, yes?
Yes.
Okay, yet, I find that solid objects don't pass through each other. If the atoms themselves are mostly nothing, shouldn't they just, I mean, the likelihood, right, that the nuclei would, which, you know, the nuclei have almost all the mass, that they would encounter each other is very remote, right? So shouldn't I be able to just like put my hand through the table, right? I can't. And do we know why we can't?
The electrons get in the way.
The electrons get in the way. The electrons obey the Pauli exclusion principle, which states that they cannot occupy the same quantum state, which means the electron clouds don't overlap, right? They're like, right? So when I touch the table, I'm actually just, it's just my electrons in my hands touching the electrons in the table, right? Okay? So I started thinking about this, right? And I was thinking in terms of normal tachyon variances, right? And integrating the normal way, which is in positive time without imaginary time, right? So then I turned that on its ear, right? And I started integrating in imaginary time, which means that we have negative time tensors, right? You know what I'm talking about, right? Okay. And so I reevaluate the Hamiltonian for the tachyon invariance, and I realize it just jumps right out on the page for me, right? I realize that with enough tachyon confinement, okay, and by how much, I'm talking about energies into the millions of electron volts, okay? With the proper tachyon confinement, I can get objects, solid objects, to pass right through each other. Like, yeah? Okay. Now, the problem is with my demonstration is that I can only do this with objects that are identical. Okay? Just because, I mean, you understand, I don't have the tachyon confinement necessary yet to do this with a full scale, you know, like Beamer going through Volkswagen or something like that kind of thing. Okay. So, but I know what you're thinking. Okay. You're thinking, why is he teaching high school physics? And you're also thinking, they're just going to bounce off each other. Okay? No. What I'm going to do is I'm going to send them into this. I'm going to send them into this thing with different velocities. So you'll know which one is which. Okay? So I'm going to send this guy in here slowly. I'll send this guy in fast. And the fast one goes out that way, the slow one goes this way, right? Okay, they went right through each other. Watch again. Slow, fast. Fast one goes right on through. Waiting for the slow one, there goes the slow one, right? Now, the thing I think would be cool, okay, is that the transmogrifier will allow you to, that's kind of loud, right? Okay, it'll allow you to, if you're like in a tunnel or something like that, right? And you want to like pass somebody, you can just go right through them, watch. It's like slow family car, fast Beamer coming along, Beamer goes right on through, slow car goes right on through, right? Yeah? You see that? Slow car, and it's just like, meep. Fast car goes right on through, right? You probably feel like a little something, wouldn't you? Just kind of like a little boom, you know? Okay. I was just kidding about all that stuff. This is just a fake, that's just a fake box, okay? This collision was inelastic. This collision here is elastic. These are like, don't like each other magnets. And what they do is, since they have the same mass, the solution that solves and gives the same kinetic energy before and after and the same momentum before and after is that they simply trade velocities. It's like, I love that. It's like, stop. Okay. So, you know, all of those tricks, right? It's like, woo. Isn't that fun? They just trade velocities. That works, doesn't it? You can look at the solution in the book. We don't actually learn how to do for IB, right? You can look at the solution in the book, but they solve it. What? Well, it's because it's elastic, is why. Okay, and then they even solve it. If you want to look at that section in the book, solving elastic collisions when they have identical masses, the solution is actually trivial. Okay, but it makes sense, right? You have the same amount of stuff moving the same speed, right? So therefore, energy is the same, and therefore momentum is the same because they trade, right? Okay, so that was yeah. A bit of a deception, wasn't it? Yeah, there we go. There. Okay. So this is a continuum. We've got elastic, we've got inelastic, right? Elastic collisions, KE is conserved. If it's perfectly elastic, then kinetic energy is conserved. And if it's inelastic, the kinetic energy is not conserved. Okay. One cool thing about this is that elastic collisions are actually reversible. Okay. Here, I'll do it again. Okay. Here, you're watching it forward. You're watching the movie forward. Now I'm going to play it backwards. Same exact thing, right? Okay. So if you could put a big spring bumper on your car, you could run into things. And if everybody had a spring bumper, your car would look the same before and after a collision. Wouldn't that be good? Yeah. There is one drawback, though. We'll talk about that drawback. And this is why spring bumpers are not only not put on cars, but they're also illegal to put on cars. Okay. One drawback might be that, like, if you run into a parked car, you like then slam into the car behind you, and stuff like that. Right? It's like, woo, whoa. There we go. Right. Okay. And then let me just show you an inelastic collision. I can make this collision totally inelastic. It's like, yeah, it stopped moving. Before the collision, there was kinetic energy. After the collision, there was no kinetic energy. Now, if you saw that backwards, you would see these guys sitting still. Then suddenly you'd see them go vibrate, and then they'd fling themselves apart with disparate velocities, yes? Yep. Yeah. You would know you're seeing it backwards. Or how about your car? You see a car all smashed, right, around a telephone pole, right? Then you see it unsmash itself from the telephone pole and fling itself back onto the road, going 60 miles an hour, God forbid, right? You would know you're seeing it backwards, wouldn't you? So that is an inelastic collision, okay? Cars are purposely designed to be inelastic, okay? So like cars are purposely designed to be inelastic. Why do you suppose?
So that people don't die in a crash?
Yeah, it turns out you want the car to absorb the energy. You don't want the people in the cars. So back in the day, by the way, they built cars to be strong so they'd survive crashes, okay? And the cars survived, but the people in them did not, okay? Now the strategy is the exact opposite. They build cars to crumple. In fact, cars are strategically designed to crumple. Frame parts that could be made stronger are made strategically weak, okay? My Volkswagen Rabbit had this little piece that connected the firewall to the rest of the car to the front bumper. And instead of being a piece of tubing, you can take a straw and jam it through a potato if you do it right. Okay, tubing is an amazingly strong thing, right? Instead of being like tubing like this, they made it like a flex straw. They put little corrugations in it like that so that when it hits something, it would actually be pretty strong, but it would also crumple. Hello. I did change rooms.
He's already
What? Tate is here. Do you want to talk to him? She just wants to know if Tate's here. Yes, he is. Bye. That's all right. Okay, so cars are designed strategically, and you hear these stories. You hear these stories where people say, gee, it was a small accident, but it cost so much money to fix, yes? That's because once you start to crumple the car, all the parts of the car between you and the front bumper are all designed to crumple in a strategic way. First this crumples, then this crumples, then this crumples. Okay? And so that's actually a good thing. So basically the strategy for getting people to survive accidents is to surround them with something that's pretty strong and rigid, right? Then inside that cage, as it were, okay, you put airbags, you put restraint systems, right? And actually, I think it's pretty complicated, right? They have a pre-tensioner. So when an accident occurs, your seatbelt will actually tighten up on you. It'll pull you back in your seat. Then the airbags deploy because your body's now in the correct position and it won't decapitate you, for example.